welcome all of you. In the last class, we started discussing about solid state NMR. I introduced the term, new terms, which gets reflected in the NMR spectrum of solids called dipolar couplings and chemical shift anisotropy. These two terms, I said, they get averaged out in the solution because of the rapid tumbling motion of the molecules. They will not be seen. So, in the isotropic spectrum, we get only chemical shifts and J coupling. Whereas, in the case of the solids, due to its rigidity and there is no translational motion, most of the time, there could be some rotational motion. We are going to see all these interaction parameters like CSA, that is chemical shift anisotropy, and dipolar couplings. And they are all direction dependent. That depends upon term called 3 cos squared theta minus 1 by 2. And they are also depends upon how they are oriented with respect to the external magnetic field. For example, 3 cos squared theta minus 1 by 2, if you take, depending upon theta is equal to 0 or 90, the dipolar coupling strength can be 2 or minus half. It can change its sign. Strength can change. So, there are in a given sample, in a solid sample, microcrystalline or amorphous, or in a powder sample, let us say, in a powder sample, there could be infinite number of microcrystals present, various possible orientations are present. As a consequence, each crystalline orientation gives rise to a spectrum. Finally, all of them are unresolved and gives rise to what is called a broad powder pattern. And I showed the example for a dipolar coupled case, when there are dipolar coupling, how we get a broad hump by taking one of these internuclear vector, and when we changing its orientation, how the splitting changes. We saw that. Finally, the overlap of all those things give us to what is called a powder pattern. This is what we discussed a lot. And of course, we came to know that we understood that studying in the solids has a lot of advantages. We get more information which you miss in the solution state, like CSA and dipolar coupling. They give rise to more additional information about the molecules. This is useful to understand in the case of solids, because some samples which are not soluble or some polymorphism etc., which you can't study in liquids, you have to study invariably in the solids. So, solid state NMR is very useful. So, we discussed about dipolar coupling a lot. Today, we will start with chemical shift anisotropy now. Okay. This is chemical shift anisotropy. Why do this chemical shift anisotropy comes? It comes because of spherical electronic charge distribution in atoms or molecules. I mean non-spherical charge distribution. Well, if the charge distribution is not spherical, then you can think electron density as a ellipsoid, more like an ellipsoid like this, and elongated along the bonds usually, or non-bonding pi orbitals. So, electron density can be treated like a ellipsoid like this. Okay. Now, the resonance frequency gets affected depending upon the orientation of this electron cloud or in the orientation of ellipsoid. If the ellipsoid is in this direction, there is one value. If it is in this direction, like similar to dipolar coupling, the direction of the orientation of the ellipsoid gives rise to different chemical shifts. How they are oriented with respect to magnetic field has different values. The orientation dependence of CSA, chemical shift, is what is called CSA. See, this orientational dependence of chemical shift is what is averaged out in the solution state, but this is present fully in the case of solids, and this orientation dependence is CSA. Okay. So, now discussing more about the CSA, you should know that it is a 3 by 3 tensor. It is a second rank tensor. All NMR interaction parameters are tensors. They are all tensorial interactions. And this has a symmetric part and antisymmetric part. The symmetric part of the chemical shift consists of 6 independent components. Okay. It is a symmetric tensor, means because only we have 6 components here, 3 diagonal and 3 off diagonal term. This is anyway symmetric, does not matter. So, you are going to have only 6 independent components of the chemical shift tensor. Now, we can possible to express this chemical shift tensor in a particular coordinate frame such that all these off diagonal elements can be removed. They have become diagonal. you have understood about diagonalization of the matrices. Exactly similar to that, we can express in a particular coordinate frame where we can get only diagonal terms, half diagonal terms are not there, they will vanish. So, in which case you can represent CSA like this. This is a beautiful drawing. You can see this is the ellipsoid, which is CSA ellipsoid. Now it has three possible. This is the z axis sigma z orientation in the magnetic field in the laboratory frame. In the molecular frame, I can consider three orientation sigma 1 sigma 2 here, means in this direction perpendicular to that, and sigma 3 in this direction. And three possible orientations I call it as sigma 1 sigma 2 and sigma 3. These are the three terms in three different directions of CSA. And now when I diagonalize the matrix, all these off diagonal elements are removed and we are going to get only three terms called sigma 1 sigma 2 and sigma 3. These are the three terms which you are going to get when we diagonalize this thing. And the principal, these are called principal components and it is called principal axis system. This is the three chemical shifts. When it is expressed like this in the diagonal form, it is a principal axis system and these are called principal components. Okay. Now you may ask me a question. This is much more, of course, most of you have been knowing in chemistry. Why CSA is orientation dependent? The molecules have different definite three-dimensional shapes. And when you see the certain electronic configurations are preferred over others, if you look at the molecular structure. The molecular orbitals and crystallographic symmetry decide about the orientation of the magnitude of CSA. If the CSA, which is larger, whether sigma 1 is larger, sigma 2 is larger or sigma 3 is larger, how it is orienting in a different direction, this is dictated by molecular orbitals and crystallographic symmetry in the molecule. Take for example, in a benzene ring like this, if you have this direction is sigma 1, this is 1, here de-shielding takes place, there is easy mixing of ground and excited states takes place in this orientation. Similarly in this orientation. If you consider make it horizontal like this, then what will happen? In this case, there is no mixing of ground and excited states. This is what happens. So different types of chemical shift anisotropy are present. For example, consider a molecule like CH4. Here sigma 1 equal to sigma 2 equal to sigma 3. All the three principal components are the same, identical, they are equal. You know why? Because the molecule has a spherical symmetry. Shielding is similar in all the three dimensions, in which case chemical shift anisotropy is 0. If you look at the so what I am trying to say is the chemical shielding anisotropy is also dictated by the symmetry of the molecules. In this case of CH4, there is spherical symmetry. As a consequence, sigma 1 equal to sigma 2 equal to sigma 3. And there is a reason is that shows there is no CSA at all. Go to a molecule like this, ethylene. It has a non-axial symmetry. That means axial symmetry is different, non-axial symmetry is different. Okay, you know that. Of course, you know when you understand matrices and everything, you know what is the axial symmetry, AT is equal to minus of A, all those things you would have understood. I don't want to go into the details. Remember, there is in the symmetry you can have axial symmetry and non-axial symmetry. If there is no axial symmetry for this, there is shielding in all the three possible directions are different. You have sigma 1, sigma 2 and sigma 3, all are present. The kings here correspond to three principal components of the chemical shielding tensor. Okay. So that is a molecule which has a non-axial symmetry. All the three components in the chemical shielding anisotropy tensors are present. Consider a molecule like this, acetylene. It has an axial symmetry along this axis. When there is axial symmetry, then what is going to happen? It has only two possible orientation. Okay. The maximum shielding is in the direction perpendicular to it. This is the direction parallel to it. Why this intensity is larger? In the perpendicular direction, there are n possible orientations to internuclear vectors. As a consequence, it has larger intensity. So this is a maximum here in the perpendicular this thing. Here maximum shielding is there. This is molecule in the parallel has maximum shielding. Here maximum de-shielding. And this is the way For a molecule having axially symmetric tensor, this is the pattern for CSA. Remember, this is the pattern for CSA. So, just to brief you about the axially symmetric tensor, which I do not need to go explain in detail. It is axial symmetry defines about the symmetry around an axis. When do you say an object is axially symmetric? You would have studied in your matrices. Object is axially symmetric if its appearance is unchanged, if its appearance is unchanged when rotated about an axis. For example, on this axis I am going to rotate. This appearance of this object will remain unchanged. That means this molecule has an axial symmetry along this axis. You understood? Similarly, depending upon the molecular structure, you can find out the molecule whether it has axial symmetry or not. So, based on the axial symmetry and axial asymmetry, we have two different types of powder pattern for chemical sheet anisotropy. This is for axial asymmetric tensor, this is for axially symmetric tensor. So, now chemical shift anisotropy for an axially symmetric tensor if we consider, and I have example of an ellipsoid like this. There are three possible orientations like this. If same acetylene is taken, if the long axis the ellipsoid is in the direction of the magnetic field like this, then this is the chemical shift. If the long axis the molecule is making an angle with respect to magnetic field like this, then this is the chemical shift. If the long axis of the ellipsoid makes an angle 90 degree perpendicular to the magnetic field, its chemical shift is here. But in reality, in the case of solids, all possible orientations are present. As a consequence, you have chemical shifts here, 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 everything is present. So, in reality, all of them will overlap and you get a pattern like this. This is called a powder pattern. This is the powder pattern for axially symmetric tensor. Okay. Now, for axially asymmetric tensor, how does the powder pattern come? Look at this another simple molecule which has assume it as axially asymmetric tensor. Symmetry is not there, it is axially asymmetric tensor. Then depending upon its orientation of sigma 11 and sigma 2 to sigma 33, this is the molecule, let us say. Sigma 11 when it is oriented like this, sigma 22 is oriented like this, sigma 33 is oriented like this, then you have, see, look at the molecule, once it is oriented like this, once it is oriented, once it is plane. Then different chemical shifts are there. One's chemical shift here, here and here, depending upon the direction of orientation of the ellipsoid with respect to the external magnetic field. As I said in the previous case, all possible orientations are present, overlapped, and it gives a powder pattern like this. This is the powder pattern for axially asymmetric tensor. So, different conventions are there for defining CSA, but you do not need to worry about it since we are not going to discuss. Just to tell you, generally this is delta 11, delta 22 or sigma 11, sigma 22, sigma 33, and when delta 11 is larger than 22 and larger than 33, this is one standard convention. When you get axially asymmetric powder pattern like this is called sigma 11, sigma 22, sigma 33 here, and this is one convention. This is another convention called Haberland convention. Here it is defined in a different way. It is just to tell you, when you get axially asymmetric pattern, you will have three different kinks like this. Each of them pertains to one sigma 11, sigma 22 and sigma 33 orientations. So, we do not need to discuss, there are a lot more to discuss about it. I just want to tell you. I want to introduce one new term called skew term, skew of the tensor. It is a measure of amount of and orientation of the asymmetry of the tensor. If the tensor is asymmetric, how much of the measure of amount of the asymmetry and orientation is given by skew of the tensor. For example, if it is a non-axially asymmetric tensor, you can find out the value of k with some expressions are there. You can easily find out it is axially asymmetric, what is the asymmetry parameter. For example, axially symmetric tensor, if it is like this, let us say this is asymmetry parameters plus 1, it is given as k asymmetry parameter. If instead of plus 1, if it becomes minus 1, what is the difference here? You see, this thing completely gets reversed. The asymmetry skew of the tensor defines its orientation. So, here skew became negative, the orientation changed, that is all. Okay. This is the way you have to define skew of this tensor, skew for non-axial and axially symmetric tensor. Now let us look at the 13th spectra of molecule in liquid and solid phase. How does it go? We don't do much about proton in the routine analysis, except there are many stalwarts in NMR who are doing enormous research to get the sharp lines in NMR to reduce the internuclear interaction strength, reduce the line width to get sharp lines. Okay. But by and large, most of the application is concentrated only on carbon 13 and other X nuclei instead of proton and fluorine. Let us take the example of the carbon 13 NMR spectra of a molecule in a liquid and a solid phase. Some molecule, I do not know what the molecule. Let us say I take the carbon 13 spectrum of that in a solution state. I dissolve the sample in a solvent and record the carbon 13 NMR spectrum. You see, all these lines are sharp. The same molecule, put it in a solid state, in a static solid, without doing anything, put the sample in a powder form in a NMR tube or whatever it is, put it in the magnetic field and record the spectrum of carbon 13 NMR spectrum. This is what you are going to get. Look at this, the single sharp line appear like this. What do you understand from this? See, all the parameters are orientation dependent and the value vary with the time, I said. So they are all anisotropic. Now the anisotropy here is getting reflected. This one, this particular peak, and in a given molecule there are different carbons. Each carbon can have a different asymmetry. One can be axially symmetric and other can be axially asymmetric. So this particular carbon, it means from the NMR spectrum itself, looking at it, I can tell you it is axially asymmetric. You can look at it. This is what we understood axially asymmetric pattern. This carbon is axially asymmetric. Look at this one, this carbon. It has a orientation like this. It is axially symmetric. Similarly, it has two kinks here. If you can look at it carefully, if you look at it carefully, there are two kinks here and here. Okay. That means this has two carbons here which are overlapped. Both are axially symmetric. And other one again axially asymmetric here. Like that, you can even get the information about axial symmetry and axial asymmetry just by looking at the spectrum of the molecule. At this carbon side, I can say there is no axial symmetry. Like that, you can discuss. So all this gets reflected in the anisotropy, gets reflected in the NMR spectrum, in especially non-spinning sample if you take it. Now with this, we can just come to a fallacy. After understanding some basic concepts about the parameters which are responsible to make the NMR spectrum of a solid very broad, there is a fallacy. Spectrum in liquids give good resolution. We saw very sharp lines, easy to analyze, but information is lost. Most important CSA, because in the previous example I showed you, this will tell me about the anisotropy and I can tell you what is the charge distribution at the site of this carbon. So all this information are present. So that information is going to be lost in solution. But in the solids, we have all this information, but there is a problem in extracting it. In the previous spectrum I showed there are only 4 or 5 carbons. In reality there are many carbons, lots of anisotropies are present. Each carbon has different types of anisotropy and they are overlapped, gives us a broad peak, very difficult to extract the information. So it is a fallacy. Spectrum in liquids gives good resolution, but information is lost. In solid, information is present, but difficult to extract. So we had to overcome some of these problems. So as a consequence, the NMR spectrum or experiments in solids can be broadly classified into 2 categories. I mean, this is my way of understanding. It need not be seen in the books. One is experiments to manipulate the interaction parameters, homonuclear dipolar couplings, heteronuclear dipolar couplings, CSA, etc. I can manipulate the interaction parameters such that all of them are removed and get a spectrum similar to that of liquids. See, in the case of solids, if you remove everything, all these anisotropic parameters, it is similar to liquids. That does not mean you can dissolve it in the solvent and do it, retaining its solid form. If I somehow design the experiment to manipulate these parameters and remove it, then I get a spectrum, isotropic spectrum similar to liquids. Okay. So experiment to get resolved spectrum is one thing like this, removing all the parameters. But that I can reintroduce these parameters. You understand the interesting phenomenon. The lines are broad, I remove it and get the resolved spectrum. But then selectively I can bring back these parameters so that I can get it reflected in the spectrum and I get the information. So spectrum will still retain high resolution character plus information from one of the parameters which I am interested can be obtained. So like this we can have different broad classification of NMR experiment, and each of these experiment number of techniques are available. Many number of 1 and 2 dimensional NMR experiments have been designed to understand and get the sharp lines, high resolution spectrum in the solids. Now to get the sharp lines in the spectrum of solids, what I have to do? I have to retain the solid in its form plus remove the parameters. It is interaction parameters, anisotropic interaction parameters like CSA, DD, dipolar coupling, etc. How do I do that? First, you should understand for spin off nuclei, dipolar coupling and CSA have term 3 cos square theta minus 1 by 2. So let us look at this equation. This is the equation for dipolar coupling. I am not right. I will come to the CSA later. For the equation for the dipolar coupling is given by this. Dij is the dipolar coupling between Na2 nuclei I and J. It is given by gamma I gamma j into H cross or Rij cube into half of 3 cos square theta minus 1 by 2. Okay, half into 3 cos square theta minus 1 and 3 I1z I2 ijz minus I1 dot ij. There are 3 parameters here. Okay, 3 multiplication. Now 3 terms are multiplied one by one another. Look at this one here. Okay. Look at this one. This is one term, another term and another. All the 3 terms are multiplied. What does it mean? If I have to remove dipolar couplings, what should I do? Make one of the terms 0. Then they are all multiplied. Automatically dipolar coupling becomes 0. One way to remove, right? So like that, based on this equation, we can devise the methods to minimize large anisotropic interaction in the solid state. So because same parameter cos 3 cos square theta minus 1 by 2 dependency is there for CSE also. Whatever happens to solid state for the dipolar coupling, of course except this and this, it happens for CSA, especially this dependence term. If I can reduce dipolar coupling and remove dipolar coupling based on this by manipulating this term by some method, same thing I can do for CSE also. That is what it means. Now go back to this equation. I can introduce a term called, one important term called dilution in solids. Okay. See, look at this one. Here Rij cube. Rij cube is in the denominator. That is what I wanted to say. It is a situation when you look for the low gamma nuclei like carbon 13 and carbon 13. If I want to see 2 carbon 13 which are close in space, that is, what is the probability? Probability of seeing any 2 carbon next to each other is 1 in 10,000. This 1% abundance. Carbon in its carbon 13 state is for any one of the carbon is 1 over 100. If there are 2 carbons together, if I have to see both the carbons in the carbon 13 state, it is 1 over 100 into 1 over 100. It is going to be 1 over 10,000. So Dij scales by Rij cube. Okay, inverse of Rij cube. So larger the Rij, Dij becomes small. Now if I consider homonuclear low 2 coupled spins, low gamma nuclei like nitrogen 15 or carbon 13, the abundance is so small, what is the probability of seeing them together? 0, close to 0. I don't say 0, very very small, extremely small. For example, 2 carbon 13 in carbon 13 state is 1 in 10,000. 2 nitrogen in the nitrogen 15 state is 1 in, nitrogen is 0.037, so much smaller. That means, in other words, I can say they are not close in space because that possibility is not there, very low. So I can say this is Rij is infinity. Rij is infinity between 2 carbons to be seen in carbon 13 state. So the spatial proximity I will call it infinite. So Dij scales as our Rij cube means for low abundant spins, I can say Rij is infinity. As a consequence, dipolar coupling goes to 0. I don't have to do anything. Nature is helping me because two carbon 13s probability of seeing them together in carbon 13 state is so close, so low probable, 1 in 10,000, I can consider them to be infinite distance, separated by infinite distance. So that can automatically help us. So that is the reason why carbon 13 natural abundance dipolar coupling are rarely seen. Very rarely it is seen. Now another thing can happen. Carbon 13 proton can have a dipolar interaction. That's possible. Carbon 13 is ruled out. I agree. Probability is low. Carbon 13 proton dipolar coupling can be present. But it is a heteronuclear dipolar coupling. Heteronuclear interaction strength is small compared to homonuclear dipolar coupling strength. Then I can remove this by high power decoupling. That is possible. And how do you remove it? There are varieties of decoupling schemes available. I can use them and start removing the dipole interaction, heteronuclear dipole interactions. It is possible. Okay. So protons continuous wave decoupling is normally adapted if you want to remove heteronuclear dipolar couplings. What I will do is I will look for the carbon 13 or nitrogen 15, any less abundant spin, decouple proton and look at the spectrum. That is what we do. That is called a continuous wave decoupling. Continuously I am applying the radio frequency power to remove the interaction strength. Take for example a glycine molecule. It is a glycine. 13C spectrum of glycine where 13C is enriched in the CO state. In the CO position, this CO carbon is 13C labeled. If you look at the spectrum of CO, no decoupling is done. Simply record the spectrum, no decoupling in a just static sample. Look at the carbon 13. Signal to noise ratio is like this, very broad. And what we do is we can do decoupling, where this is what here done without decoupling here, no decoupling is done here. But now what we are going to do is we are going to do the decoupling at the same time, we acquire the signal, at the same time we do the decoupling. This is signal acquisition. Continuously I am breaking the coupling between carbon and proton by applying decoupling power. This is what it is. Now if I do the decoupling, with decoupling there is very interesting thing which I wanted to show you. This is the carbon 13 spectrum of glycine. We saw a big peak for carbonyl carbon, okay, a big peak for carbonyl carbon. There is another carbon CH2. Where is that peak? Look at it, it is here, invisible without any decoupling. Now on the other hand, when we do the decoupling, even just put it in a static state, we already see this thing, powder pattern, 3 kinks are seen. Okay. So look at the signal to noise ratio and look at the carbon 3 peaks, the powder pattern of this CO carbon is very clearly seen. Interestingly, the C alpha which was not even visible started visible here. So decoupling helps. If you remove the heteronuclear dipolar coupling, you get better spectrum. So most of the time we can, while detecting carbon 13, we do decoupling. Okay. So if there is heteronuclear dipolar coupling, we remove by what is called heteronuclear dipolar decoupling. With this, we will go back to this DIG, dipolar coupling expression. We understood this. It is called dilution in solid. Infinite distances we can think of between two naturally abundant carbon 13 or nitrogen 15 in their nitrogen 15 state or carbon 13 states. So this one factor which can make dipolar coupling among two dilute spins, homonuclear spins, 0. What about these two terms? There are two other terms. Can I not make them 0? Is it possible for me to make this term 0? Is it possible for me to make this term 0? This is called space part. Okay. This is space part and this is called spin part. Now I can remove the dipolar coupling by doing something in the space part. or I can do something to the nuclear spin in the spin space. Both I can do individually or both simultaneously. I can do both. All is possible. Okay. So then we can devise the methods to eliminate or minimize the large anisotropic interaction in solid state. We can with this understanding, especially the dominant interaction in the dipolar coupling I said for spin off nuclei. So how do you remove these interactions? I can deal with the space part, or I can deal with the spin part, either of them. Okay. Now in the case of the spin part, what we are going to do is, we put this sample, this let us say that the internuclear vector, put the sample at an angle in the magnetic field called magic angle spinning. At an angle we put called magic angle and start spinning the sample rapidly. What will happen there? I will come to that later. I can do this, put a sample at an angle called magic angle and rapidly rotate the sample. Then average interaction that depends upon 3 cos square theta minus 1 by 2 terms can be eliminated. The dipolar couplings depends upon this, especially the heteronuclear dipolar couplings depends upon these terms that can be immediately removed by putting the sample at an angle and rapidly rotating at high speed. This we can do spatial rotation. Physically we can rotate the sample. That is why it is called physical space. I can manipulate in the physical space. Alternately, I can use multiple pulse sequences. I can do some spin gymnastics. The same thing what I said, I can make the sample rotate at magic angle to remove. I can do the, instead of rotating the sample, I can rotate the spins. I can do some spin gymnastics, make the spins to undergo rotations like this. How I tell you as we go ahead how we can do that. And I can do the spin gymnastics that can also eliminate dipolar couplings in the spin space. Again, everything, all interactions cannot be eliminated. Using these things we can eliminate homonuclear or reduce, minimize homonuclear interactions like homonuclear dipolar couplings. Whereas magic angle spinning we can remove or minimize heteronuclear dipolar couplings or CSA. We can do that. So depending upon whether you use physical rotation or spin rotation, if you are using physical rotation, you can remove heteronuclear dipolar coupling and CSA. If you are using multipulse, we can remove homonuclear dipolar couplings or reduce quite a bit significantly. So these two things we can adapt. Okay. So next I will discuss about magic angle spinning. What is the magic angle spinning? How it is done? How it will remove anisotropic interactions of the second rank tensors? Everything we will discuss in the next class. But today, continuing with the solid state NMR, we discussed about chemical shift anisotropy, patterns of the chemical shift anisotropy, how we get the powder pattern for CSA, if this tensor is axially symmetric, how do we see that if this tensor is axially asymmetric, and we discussed about the skew factor which also determines this the appearance of the powder pattern. And of course, we knew how the chemical shift anisotropy comes into the picture. It is because the charge distribution is non-spherical at the site of the nucleus. You can think of as an ellipsoid, and the direction of orientation of this ellipsoid in different directions gives rise to different chemical shifts. And it is a tensor which has 6 components, 6 elements. It is a symmetric tensor. So basically we can diagonalize it and get only 3 principal components, sigma 11, sigma 22 and sigma 33. And for asymmetric axially asymmetric tensor, all the 3 sigma 11, sigma 22, sigma 33 are different. For axially symmetric tensor, sigma 11 and 2 of them are equal and 1 of them are different. Okay, that is the important thing you should understand. For axially symmetric tensor, all the 3 components sigma 11, sigma 22, sigma 33 are different. For axially symmetric tensor, 2 of them are equal and 1 of them is different from the 2. That is what we understood. And I said we can manipulate the dipolar couplings by spin space or physical space to eliminate some of the interaction tensors. Physical rotation, physical space interaction manipulation can remove heteronuclear dipolar couplings and also CSA. Heteronuclear dipolar coupling can also be removed by decoupling. Heteronuclear decoupling with a continuous wave of RF, continuous RF pulse, high power pulse. And of course, these two all can be combined together, need not be individual. They can all go together also. All this experiment can be done together. So, this is what we discussed a lot about these things. We took some example for decoupling, how we see the anisotropy of the different peaks. If it is a non-spinning sample, stationary solid, if we take, look at the carbon 13 spectrum, the anisotropy gets reflected in the carbon 13 spectrum, and we could see whether at the site of the particular carbon there is axial symmetry or not. We could understand. So, a lot of things we discussed about CSA and methods of elimination, everything. We go into the individual methods like magic angle spinning and all other things in the next class. So, we will continue further. I am going to stop here. Next class we will start with magic angle spinning. Okay, thank you.